Okay, we've covered all the material from first order separable DEs, and now we're going to look at a bunch of problems. This is section 2.9, and I'm just going to get you started on each one in case you have troubles with it. And so let's look at them together. So exercise number 1 says let y of t is the amount of algae in grams in an aquarium. So this is 2.9.1, and y of t is the number of grams of algae at obviously time t. Okay, so we've got some initial time. And what are we told? We're told that the algae multiplies at a rate of 5% per hour. So in other words, the rate of increase of this population is 5%, or that would be the same as 1/20th y. Agreed? The amount of change is 5%, or 1/20th of what's there. So you know that. And you know fish eat the algae at a rate of 3 grams per hour. So this is happening, but also at the same rate. I shouldn't say at the same rate, but going on at the same time, this is also happening. The rate at which it's being eaten is 3. Notice we don't have to put 3t there. It's just 3 because this is already the rate. The rate is -3 because it's decreasing. Okay? And so that's going on. And so then what's the question? Initially there are 10 grams of algae in the tank. So we know at time equal to 0, y is equal to t. And so you need to do the following. First of all, write down a differential equation that models the situation above. Well, I guess we've already got that, right? So you can write it like that. Or let me give you a little algebraic trick. If you write this as 1/20th y minus 60, now you've got these things connected together, and it'll be a little bit easier to go from there. Okay, so either like this or like that. Of course, they're the same thing. Solve the DE. Well, I'm not going to solve the whole thing for you, but you see this is separable. So now you can go dy over y minus 60 is equal to 1/20th dt, and of course you can go from there. Agreed? So you can go from there. Once you have that solution, then you can find it's going to have a constant of integration, and once you have that constant, you can determine that constant by setting the fact that y of 0 is equal to 10, so you'll be able to find it, and once you find that, you'll be able to determine when will all the algae be eaten. Okay, I'll let you go from there. And then sketch the graph, and then change things slightly. What would happen if instead of initially there being 60, what would happen if there were 100 here? I asked that question, and I also what happens if there were 10, and then I ask you to basically ask what happens for all. No, I'm sorry. If the initial condition were instead of 10, if there were initially 100. So if there were initially 100, then what would happen? Or if there were initially just look at the questions. It asks you to play with those a little bit. Okay? And basically you want the long-term behavior. What happens to the amount of algae in the tank? And finally I say go ahead and use a phase diagram to get the answer that way too. So you can do that. Okay? So that's all number 1. Number 2. Number 2 is a mixing problem. We're going to have a lot of these later on in the course, but this is just the first one. You have a tank with 600 gallons of water. I always like to draw a picture when you have something like this, just to kind of get all the information in a picture. So you have 600 gallons of water there. And in that water you have 450 kilograms of salt. Okay, pretty salty water. Okay? pure water is run into the tank. So you have pure water running into the tank like this. I like to just draw a little picture like that. And it's coming in at a rate of 15 gallons per minute. And then the salt solution is running out of the tank at the same rate. Okay, so do you agree that the water level will stay the same, but it's pure water that's coming in, and it's the solution that's leaving, and I think I say it's all being mixed constantly with a blue spoon, okay? Is it important that it's a blue spoon? No, it doesn't have to be blue. Is it important that it's a spoon? No. Is it important that it's mixed? Yes, it's very important that it's mixed. Otherwise, you'd have to make a much more complicated model where you'd say that this would be more pure water up here and this is more of the solution down there, and there's some sort of a gradient, okay? So that would make it much tougher, which we could do, but we're going to make it a simpler problem by assuming you're always mixing it, it's always being mixed, and so the solution is homogeneous throughout the whole thing, okay? So that's an important assumption. And the question is, how many kilograms of salt remain after 20 minutes? So it's very similar to the kinds of problems that you might have done in algebra class in high school, where you have something like, I remember doing these, where you have solutions and you put in more salt, you put in more water, and you want to know what the solution is. The difference is that this is a continuous process, right? There, it's you put it in a gallon at a time, and after putting in 5 gallons and taking out 3 gallons, then what's the solution? So it's always discrete amounts, whereas here it's a continuous process. That's the real big difference between algebra problems and calculus problems, is that you can do these continuous problems with the aid of calculus, with the aid of differential equations. Okay, so anyway, let's start off, and remember that the most important way to begin each of these problems is with the word let. So what are we interested in? We're interested in how much salt is there in this tank. So let's let y of t be the number of kilograms of salt in tank at time t. Okay, very important that you do that. It's hard enough to do these problems anyway, and unless you have that right staring in your face, it's hard to see exactly how to get started. Once you have that staring in your face, then you can say, oh, okay, what's the rate at which that salt is changing? That's what dy dt is, agreed? dy dt is the rate at which that amount of salt is changing. So I'll get you started on this again. The way to do these problems is to first ask, what's the rate at which the salt is entering, and what's the rate at which the salt is exiting or leaving the solution? And so for this one, notice it's pretty easy. There's no salt coming in at all. Water's coming in, but no salt. So there's this, and y is the amount of salt, right? It's not the amount of water, it's not the amount of fluid, it's not the volume, it's the amount of salt. So that's going to be a big old fat 0 there. And what's the rate at which it's leaving? Well, let's see now. What's the rate at which it's leaving? The rate at which it's leaving has something to do with the rate at which the solution is leaving, but it also has something to do with the concentration of the solution, right? So the rate at which the solution is exiting is like, for example, if this were 2 kilograms per gallon, if that were just constant, 2 kilograms per gallon, and if the amount was exiting at 5 gallons per minute, then what's the rate at which the salt is leaving? Well, there's 5 gallons per minute that are leaving, and every gallon has 2 kilograms per gallon. So boom, boom, those two things go, and you're going to get 2 times 5 is going to be 10 kilograms of salt per minute. Agreed? Agreed? So you got something like that. The rate at which it's leaving is going to be 15 gallons per minute. Okay? But now you need that concentration. What's the concentration? Say, well, it's not 2 kilograms per gallon. You'd say, oh, well, let's see. It's 450 kilograms per 600 gallons. So you might first be tempted to go, oh, it's got to be 450 kilograms per 600 gallons. You say, ah, there's the concentration. But then you think, no, that's not right. That's just the concentration at the very first instant. After that very first instant, things change, right? So after the first minute or so, it's no longer 450, it's some other number. And so you think, well, heck, what's going to be the concentration in general? It's going to be this many gallons. That doesn't change because it's always 15 coming in and 15 going out. So it's always going to stay 600. Don't have to worry about that. But we need something to represent how much salt is there in the tank at time t. At the first instant, there's 450 kilograms of salt. But I need something to indicate how much salt is there in the tank at some other time t. That's going to be the concentration. And so here's the key. You think about that for a while and you think, dang it, I need something to indicate the amount of salt in the tank at time t. And then all of a sudden, you look up at what you've written down and you said, oh, that's what y is. Y is the amount of salt in the tank at time t. That's why it's so important to put this there. As I say, it's hard enough without having it staring in the face. So if you stare it in the face, it's still hard. So you say, oh, okay, here's what I want. I want the amount of salt in the tank, that's y of t, or just y, divided by the number of gallons, which is 600. And there you go. There's your concentration. So now you have the concentration. This is the concentration. And this is the rate. The rate at which it's leaving. Okay? So there you go. So you multiply those together just like those, and you're going to get the rate at which the salt is leaving, right? This is the rate solution is leaving. Okay? So the solution is leaving at this rate. There's the concentration of the solution. You multiply them together just like this, and you get the rate at which the salt is leaving. Okay? So I'll let you take it from there. Okay, that's 9.2. How about 9.3? Okay. When she heard the shotgun blast, Angela raced to the window and saw the dim figure of Mr. Smith hurry from the victim's house to his own house across the street. She called 911, and soon officers Bill and Joe arrived and questioned Mr. Smith as to his recent activities. Smith claimed he had been reading a book while sitting on the toilet and had just gotten off a minute ago. Angela disagreed. So Officer Joe took the temperature of the toilet seat and found it to be 75 degrees. So let's start right off by letting y of t equal the temperature of the toilet seat. That's the thing that's changing. Okay? And time equal to 0, I'll say y of 0 is the temp at the first reading. Okay, I mentioned that in the problem, is you let time equal to 0 be the temperature of the first reading. So I'll say t equals 0 is the first reading, time of first reading. Okay, so what happens? And found it to be 75 degrees. So you know that y of 0 is equal to 75. Okay? 10 minutes later, he measured again, and it had cooled to 70. So y of 10 is equal to 70 degrees. Okay? The temperature of the air in the house is 60. So let's let beta. Remember, we use beta for the temperature of the surrounding medium. Beta is going to be 60. Okay, temp of house. Okay, it's kind of cold. And assuming the temperature of the seat was 98.6 body temperature when he got off, okay, then what do you want to know? And also, assuming that the rate of cooling, here's Newton's law of cooling. The rate of cooling, here's the rate at which the temperature is changing. What do we know about that? The rate at which the temperature is changing is proportional. Here's a proportionality constant. To what? The difference between the temperature of the seat and the air. Well, the temperature of the seat, here it is, right there. See that? So that's just going to be Y. The temperature of the air is 60. Okay, so that's the rate at which things change. It's proportional to those two temperatures. And the question is, find out how long Mr. Smith had been off the seat before the measurement was taken. He said he had just been off of it for 1 minute. Okay, so I'll let you take it from there. We've solved several like this already, so you can solve this one, and you're going to get a couple constants, and you can use these two pieces of information to find those constants, and then you can figure out when. Well, I'll let you take it from there. I'm not going to give you any more information. Okay, so that's a good one. That's a fun one. By the way, do you recognize those names? Bill and Joe and Angela. I chose Angela to stand for Angela Lansbury. She's the actress on Murder, She Wrote. And Bill and Joe, those are the two cops in Dragnet, which it was a television show way back, and more recently has been a movie called Dragnet of two cops that try to solve crimes. So anyway, in case you didn't live through all that. Okay, 294. This is one of my favorite problems. Some of these other ones I came up with myself, but this one I found someplace. Assume the shape of a city is roughly circular, okay? So there's the shape of the city. So right away, this would not hold for the city of Chicago, which of course is on the bottom of Lake Michigan, or anything that's up against a mountain range, like Denver or something like that, or Holland or Holland, where I live, which is kind of up against Lake Michigan. But if you're out maybe in the Midwest, like Oklahoma City or something like that, where there's no mountains and I don't know, no bodies of water, nothing like that, there's no reason why that city can't just kind of spread out in all directions. So this will be a Midwest city. The shape of the city is roughly circular. So we're assuming that, and we're also assuming that the maximum travel time is proportional to the diameter of the city. Okay, so if we let m stand for the maximum travel time, the maximum travel time is proportional. Let's put a k there. I'm going to have lots of proportionality things there, so let's use k1, to the diameter of the city. So let's let d be the length of the diameter. So there's d right there. Okay, and m is the maximum travel time. Okay, what else are we assuming? Assume that the population is proportional to its area. So let's let the population is proportional. So here's a proportionality constant to its area. So P is the population and A is the area. Okay? That's reasonable, isn't it? Well, we'll get them all first. And then finally, the rate of increase of the population is inversely proportional to the maximum travel time. The rate of increase of the population. Well, as soon as you hear the word rate, you should think, oh, that's the derivative. That's the derivative of the population. There's the rate of increase or decrease. It's the rate of change. Is proportional to, so let's use K3, to the what? Is inversely proportional to the maximum travel time. So in other words, if it's inversely proportional, then you put the m downstairs rather than upstairs. Okay, so you have that. Let me make that a little bit better. Like so. Okay, so first thing I ask is, discuss why or why not each of these assumptions is reasonable. So let's think about it. The first assumption is that the maximum travel time is proportional to the diameter of the city. That makes sense, doesn't it? The maximum travel time would be the maximum time it takes to get from one spot in the city to another. And I guess if it has a good roadway network, then as the diameter of the city increases, that maximum travel time is going to increase. If the diameter is twice as big, you'd maybe expect the maximum travel time to be twice as good. You know, maybe not exactly, because maybe if it gets to be a really big city, then they'll start putting in bigger freeways and things like that. So maybe it's not quite right, but that's reasonable. I mean, right? So that's reasonable. What's the next one? The population is proportional to the area. Okay, why is that reasonable? Okay, is that a reasonable assumption? I mean, cities often have high rises, you know, in the downtown area, but then they also have a lot of businesses in the downtown area. So, you know, that's again kind of an assumption. It's not exactly right, but as you go out more, then you have less businesses, but then you also have houses that are kind of maybe close together. So anyway, you discuss that. See if you agree or can convince yourself that that's at least, you know, approximately reasonable. And then here's the last one. What about this one? The rate of increase is inversely proportional to the maximum travel time. Why would that be an assumption to make? What do those things have to do with each other? The rate at which the population is going to increase, why would that have anything to do with the maximum travel time? In particular, why would it be that as the maximum travel time increases, that the rate of increase of the city is going to decrease, right? That it won't grow as fast. Why is that reasonable? So I'm not going to give you the answer to that. You think about it. I want you to give it to me. But just think about it. What are the two different ways in which cities grow in size? One way would be by having more births that actually happen in the city, right? So people have babies and so on. That would be kind of constant. That probably wouldn't have much to do with the maximum travel time. But the other way would be what? People coming to the city, right? People moving there, okay? Why do people move to a city? It's a nice place to live, right? It would be a nice place to live. I heard that San Antonio is one of the nicest cities out in Texas and so on. So what people come to a city, the rate at which they come, that kind of depends on how nice of a place it is, and what does that have to do with the maximum travel time? Okay, so I'll let you ponder that. So the point is, once you have those three things, then you want to get one equation. In fact, what do I say? I say use the assumptions to find a differential equation of the form that dp dt is equal to some function just of p. Okay, none of these other things, just of p. So how can we do it? Let's think about it. Well, let's see. Again, I don't want to do the whole thing for you, but you've got what? You've got dp dt is k3 over m, and m is equal to k1 over d, right? And now you also have a relationship between d and a. So what's the relationship between the diameter of a circle and the area of a circle? Well, how are those things related, right? How are those things related? So that's what you have to do. You have to take this d and you have to write it as something involving a, and the area of a circle, you can figure that out and so on. So I'm not going to tell you anything more about that. You take it from there. Okay, so that's number 4. Okay, number 5 is one of my favorite problems that I made up myself. Okay, and this is number 5. And so here's what's going on. You're in a boat. You're in a speedboat. Motor on the back. And you turn off the motor. And when you turn off the motor at time equal to 0, v of t, let's say, is the velocity or the speed of boat at time t. And so we know that v of 0 when you shut off the motor is, what do I say, 30 feet per second? I can't remember. is 44 feet per second. It's 40, I'm sorry, it is 30 miles an hour. That's pretty fast for a boat. 30 miles an hour, and 30 miles an hour is 44 feet per second. Okay, you do the calculation if you want. That's 60 miles an hour is 88 feet per second. I happen to know that, so that would be 44. Okay, and 2 seconds later, it's 33 feet per second. Okay, so it's obviously slowed down. You turn it off at time equal to 0. And it's 30 miles an hour, and then 2 seconds later it's 33 feet per second. Okay? And here's what you need to do. You need to eventually find out how far that boat is going to travel once you turn off the motor. But there's some steps in between there. And so here's the things you need to assume. First of all, you assume that the only force acting on the boat is the force due to friction. Okay? There wouldn't be many other significant forces. Maybe a few little minnows bump into the boat or something like that, but otherwise frictional force with the water is probably about the only one. Or with the air, but it's all still due to friction. Okay, so that's all good. That's a good assumption. Second assumption is that the force due to friction is proportional to the speed of the boat. Okay, so here's the second assumption. The force due to friction is proportional to, there you go, is proportional to the speed of the boat. And that shouldn't be a surprise to you after our previous section in which we looked at terminal velocity and so on, right? If you're going at fairly slow speeds, such as maybe the speed of this boat, then the force due to friction is proportional to the velocity. Okay, so that's all good. The third one, Newton's second law holds. What's Newton's second law? Newton's second law is that the sum of the forces, all the forces acting together, is going to be the thing that accelerates or decelerates. Decelerates is just a negative acceleration. Is going to be the thing that decelerates the boat. Okay, so that holds. Okay, that holds for sure. Okay, so that holds. So those are all the things you know, and now you need to get basically you need to prove that you've got something of the form dv dt is equal to, let's call this k1. I'm just going to call this one k is equal to k times v. We need to get a differential equation like that. And the question, how can we do it? So let's think about it. Let's think about it. So here's the things we know. So first of all, acceleration is dv dt, right? That's the rate of change. So I have m times dv dt, there's your acceleration, m times dv dt, that's equal to the sum of the forces. Okay, that's what Newton's second law says. And we're assuming that the only force acting on this boat is the force due to friction, so the sum of the forces is just this force due to friction. So we know that. And we know that the force due to friction is just proportional to the speed. Agreed? So look at there. So that's all there was to it. Okay? So it's just a matter of tying those things together, and you get what you want. So now you can write dv dt is equal to what? K1 over m times v, right? And this thing here is just another constant. So that's just another constant. So there you go right there. So there's your differential equation, and that gets you started. And then I say go ahead and solve this thing and find v. That should be something you can do now. It's a separable dE. And then I say, when will the boat stop? And I say there, be open-minded. Okay? Be open-minded. When will the boat stop? I won't say anything more to you than that, but just allow for any possible answer there. And then finally, the last question I ask is, find an expression for the distance that the boat goes. How do you find the distance if you have the velocity? So here you're going to have the velocity, and oops, let me make sure that you're still with me here. Okay, you are. If you have the velocity, how do you find the distance? And hopefully you remember that all you do is you integrate it, right? And this will give you a formula for x of t, and you're going to have some sort of constant of integration. And once you have that constant of integration, you can say something like, oh, let's assume that x of 0, well, what do we know? At time equal to 0 is when you turn it off. So x of 0 is the starting position, right? That's your starting position when you turn the motor off. Okay, so I'll let you go ahead and do that, but you're going to get some expression there, and you're going to want, I've taught this enough that I know what kinds of problems people have. You're going to want x of 0 to be equal to 0. And so for x of 0 to be equal to 0, you're going to have to find out what value of c makes that true. A lot of times people say, oh, if I want x of 0 to be 0, I just let this constant be 0. Nope, doesn't always work that way. It doesn't here. You're going to have to find the right constant so that x of 0 is equal to 0. And once you have that, then you can go ahead and find out how far it goes. Okay, so you think about that. That's a really nice problem. Okay, and then the very last one, 296. This is an extra credit problem. This is one that I remember my calculus teacher or differential equations teacher doing for us in class. It was a really tough one. It turns out it's kind of a classic problem. And I'm just going to get you started on it. It's extra credit, but it's a really nice one. And if you want to, this particular one, I'm sure you can find online. If you just put snowplow problem or something like that, you'll be able to find it. But basically, here's let me read it. I love it because it's so simple. One day it started snowing at a heavy and steady rate. A snowplow starts out at noon going 2 miles the first hour and 1 mile the second hour. What time did it start snowing? Isn't that wonderful? It starts snowing and at noon a snowplow takes off and it goes 2 miles the first hour and 1 mile the second hour. When did it start snowing? And the only assumption is that the snowplow moves a constant amount of snow per unit time, okay? If that snowplow is really pushing, it's just pushing as much snow as it can, and it's going fast if there's a small layer of snow, and if the layer of snow gets larger, then it has to slow down because it's pushing the snow off the road at a constant rate. Okay, so that's your only assumption. So let me just write down what I have here to get you started. It's really a wonderful problem, and kudos to you if you finish it off. I'll get you started here. So let's let t equals 0 be noon. Okay, that's when it starts snowing. And let's let r be the rate of snowfall. Okay, so that's going to be in inches per hour. Okay, like 5 inches per hour or something like that. And let's let x of t be the distance traveled at time t. And let's let w be the width of the road. Okay, w is the width of the road. Okay? So here's what's key. We're told that the rate at which it pushes the snow off the road is a constant. So let's let k be the rate at which it's pushing the snow off the road. So what's the rate at which it's pushing the snow off the road? Well, first of all, you need to take the speed with which the snowplow is moving, and if x of t is the distance traveled, then do you agree that dx dt is the velocity? So there's the velocity, there's the speed. I'll just write the word speed. We're only going in one direction there, so speed and velocity are the same. So there's the speed. And now you take that speed and you have to multiply that. The speed, basically, if it's plowing down the road, then you take the speed and you have to multiply that by the width of the road, and then also by the height of the snow, right? If you take the height of the snow and you multiply that by the width, and you multiply that by the speed, and you multiply that by the time. I need to have time in there too. Do I have time? Oh, we want the rate. Okay, so we want the rate at which it's doing it. So the rate at which it's doing it is going to be the speed times the width, and the width is w. And then we have to multiply that by the height. And what's the height of the snow? What's the height of the snow? Well, to get the height of the snow, you need the rate at which it's snowing times the amount of time that it snowed. Right? So let's let T naught be when it started snowing. T naught started snowing. And so at any time t minus T naught, that's going to be how long it's been snowing. So for example, if it started before noon, so this is going to be a negative number there. So before noon would be a negative number, and so noon is, because noon is 0. See that? So it started before that. So if at 2 o'clock, and if it started snowing at 11, that would be a -1 hour. So 2 minus a -1 would be 3 hours. If it started snowing at 11 and it's now 2 o'clock, then you take 2 minus a -1 is going to be 3. So it's been snowing for 3 hours. It's snowing for 3 hours, and it snows at a rate of 5 inches per hour. So this is 3 hours. And this is, say, 5 inches per hour. So that's how high it is. So that means it's 15 inches high. And now it's 15 inches high, and say it's, say, 100 inches across. I have no idea how far it is across the road. But let's say now you multiply that by 100 inches. And that gives you the height of this, the height of this rectangle right here. Can you see it? It's 15 inches high and 100 across. So that height, and now you multiply that by the rate at which this thing is moving. And there's the rate at which it's moving right there, and that's going to be the rate at which it's pushing it off the road. So that right there is what's constant. Okay. So I'll let you just take it from there. See what you can do. See what you can do, and get help from the internet if you want. But that's a really nice problem. Okay. So you can find the exact time at which it started snowing, and it's I'll give you a hint. It's 11 o'clock, 11 hours, and so many minutes. I won't tell you how many minutes it is, but it's 11 o'clock and so many minutes before noon. Okay, not 11 hours, but 11 o'clock. 11 o'clock. Okay, very good. So those are hints to get you started on all these problems. Have fun with them. Those are some nice ones, and they just show all the different things you can do with differential equations. Notice we're doing population, we're doing temperature, we're doing snowfall, we're doing speed, all these various things you can do with differential equations. Okay.